to see how far you can get. If you guys if you guys want, I'm not going to force this issue, but if you want, you can grab out a colored pen because maybe some of your weaknesses have come out on this one as you guys were working in your groups, maybe with factoring, etc. So you might want to get out a colored pen just because you can also study from these bell works in the back, and a colored pen marking or giving yourself hints or clues or writing down some things I might teach to help you through this problem. Something to study for the future. All right. Which one's easier, x-intercept or y-intercept? Wow, I didn't expect you to say both. Yeah, I would totally agree. With part of you. I wouldn't say with all of you. Ironically, I would think the y-intercept was the easiest one. And I heard some people say that, but I heard the majority of you say the x-intercept. Huh. Interesting. Let's review really quickly what we're supposed to do. For the x-intercept, what do we know to set equal to 0? Or which one do we know to set equal to 0?
Y.
The y. And we have to find, we can say in a sense, the a. We have to find what goes with the 0 when y is equal to 0. So we would put 0 equals x cubed minus 4x squared minus 21x. So some of you answered x-intercept, and it's going to take a little bit of work. Y-intercept, what's different? Set x equal to 0, solve for the y. Why am I thinking this is the easiest?
Because all the...
Yeah. Man, I think this one's easier. As long as you can say that's a 0, that's a 0, that's a 0, and 0 minus 0 minus 0 is 0. So I liked him, right? Maybe some of you were just thinking of the hard one is when y is 0, so you said y-intercept. Be careful, that's really easy to confuse. The x-intercept is when y is 0. The y-intercept is when x is 0. So let's come back to this one. What makes this guy hard? Yesterday. Yeah, you guys are all thinking. Yesterday, when we did this one, what did I say up here in the notes that we need to be careful for? Yeah, x-intercepts, finding the zeros, factoring. And we did a little baby example down here. But why is the one in your bell work harder than the one yesterday? Even after you pull out, which was nice. It's nice that there's a shared x. If I had put a +1, some of you would have gotten really frustrated because you're like graphing. Factoring cubics. I didn't like it last year. I bet I won't like it this year. We'll see it. We'll do it. Synthetic division. We'll have some fun. But for right now, it's not that bad because an x does come out. But some of you still don't like these for whatever reason. It didn't stick in Algebra 1. But at least, A times C. What am I talking about? A is the leading coefficient. Careful. And who's the leading coefficient of x squared? 1. And C is the constant, or negative 21. 1 times negative 21. We love it when there's a 1 in front, right? Or at least we like it better. As soon as there's a 2 or a 3 or a 12 or a 25 or a 144, we start getting really sad and really mad. Or at least something in between. Right? But since there's just a 1 in front, you guys can do this different ways. But hopefully, at least some of us are able to not mental math it, like not go from here to the answers. I mean, some of you probably could, maybe 1 or 2. But most of us at least need to write this out, and then at least need to take a second to think of, hold on, what makes 21? 7 and 3. What multiplies to be 21? 7 and 3. This is my guess and check method where I just know I want 2 binomials and I'm filling them in as I go. I know probably 7 and 3. 21 and 1 doesn't seem to make 4. I know x times x. All I need are the signs. Negative 7 and a positive 3 because I need a negative times a positive to be a negative, and I need negative 7x and 3x to make the negative 4x. So what do I do now that I have factors? Wait, pause, but good. I agree. How many factors do we have? That's another mistake commonly made. Not 2, but 3. He's a factor also, right? So I have 3 quantities being multiplied, and now go ahead and use your, what do I do when I have factors equal to 0? Set each one. You guys get what I'm doing when I do this? I could write up above, but then it gets in there and it gets messy. So x equals 0. Oh, all right, sweet. X equals 0. X equals? And x equals? And typically we would write that in number order, -3, 0, 7. We could give them as actual points, right? 0, 0, 7, 0, -3, 0. That's also valid. But if we know their x-intercepts and we say x equals, then we know that those are the points on the axis when y equals 0, where the graph is hitting. Okay, not too shabby. So what if I was to give you, let's just keep going in our bell work. Ready? I want you to label this one just right underneath factoring practice. Don't worry, we'll do quite a bit of this year. But let me see, maybe you guys are a step above last year. What if I was to give you factoring practice? Zeros of, so we can still keep it under the y-intercept problem. Finding the zeros of, let's do something like, how hard do we want it? Medium? Okay. I don't like that one. I know. It's hard to come up with these. Give me a break. Oh, that's no fun. Oh, this is going to be way too easy. All right. It's going to be way too easy, but go ahead. No, you cannot factor out of 3. Ideally, you want to be able to do this by hand. You might be going to your calculator to multiply 3 times 66 and start dividing that by lots of different numbers. But if you are going to your graph, that's not a valid by hand technique. And if you are going to solver, that is also not a valid technique. You need to be able to do this by hand. If you're using it for multiplying and dividing, for right now, I'll let it go. That makes sense. Kind of. But if you're using a graph or a solver, that's not valid. It's good for checking if you ever get stuck. But draw your table, Lauren. Are you doing your table? Yeah. Got it. I do mine a little differently. I was just seeing which way you went. Okay, I'll give you guys a little bit of time just to see if you knew the direction to go. You might not have finished the entire thing, but to see if you had a direction to go. We're going to go ahead and, as a class, in some way, shape, or form, pick the one that we like the most, and I'll try to use that one. Maybe not for every single example where we ever need to do factoring, but at least for the majority of them. The way that I learned was guess and check. It works with my brain. It shows very little work. Most of the work is done in your head. For guess and check, you think about, I need to make two binomials. Probably some sort of x term, constant term, pluses and minuses in between. You look at your first term. What's my first term? Up there. 3x squared. And you think the first term comes from the f of FOIL. The first term comes from the f of FOIL. You look at the last term. As long as you've written it in proper order, ax squared plus bx plus c. What's the last term? 66. And you think of the last two, instead of the first two placements, the last two placements, the last two needs to be multiplied to be negative 66. So you can think about, I need this one to multiply to be negative 66. I need this one to multiply to be 3x squared. Now, I don't usually write this. It's just kind of in my head, but just showing you what I'm doing. And then we need to think of our outer and our inner in the sense of, oh, I've already done it weird. That was supposed to be up there. That's okay. I'll change it. I'll do it like I taught my Algebra 1 kiddos. L is negative 66. Then I have my inner and my outer. I like doing the smiley face. Ta-da! Anyway, so the outer and the inner need to add to be negative 7. So what's one way of getting 3x squared? Why not 3x and x? Does that sound good to you guys? Okay. So I think about how 3x and x could make 3x squared. What's one way of making 66? 1 times 66, 3 times 22, 6 times 11. Which one do you like better? 6 times 11. So if I just were to put 6 and 11. Now, as long as I make one of them negative, I have 66, and one of them will be negative. I have 3x squared. But what I need to check is my outer, 33, and my inner, 6. Can 33x and 6x make 7? No. It's like in the 20s or in the 40s. Doesn't work. So I have an option now. My option is to either totally scratch 6 and 11 or switch places 6 and 11. So if I switch places, now all of a sudden I have 18 and 11. What's 18 and 11 make? With subtraction? 7. Now, to make 7, who's going to be the negative one? The bigger one, 18, or the smaller one, 11? I need the 18. Well, I'm not going to put a negative there. That's awkward. Let's put a negative here. And then this one must be a dun 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 dun. All my work right there. But some of you, that's a little too much mental math. Not impossible, maybe, but it's a little too much. And if you were to have something in the front like a 12, and you're like, aw, stinks. So the front could be 1 and 12, 2 and 6, 3 and 4, or I could flip. And all of a sudden, we have lots of combinations. So some of you like doing the method where you multiply a times c. If you multiply a times c, you're going to put that in the top. You're going to have your middle b down. And you're looking for what two numbers multiply to be the top and add to be the bottom. So a times c, what did you guys get? Negative 198? Adding to be negative 7. Now, what's the dilemma right now? Factors of 198. 198. 2 and 90, are those going to be like really far apart and I need them really close together? So maybe you can start working through these pretty quickly. You guys already got some time to work. Did you find the two? What'd you get? 18 and? Oh, that's funny. 18 and 11. Stand for. The struggle is when you have the 18 and the 11, one needs to be a negative, one needs to come back to the original problem and do your 3x squared minus 7x minus 66, because this is our first is going to just kind of stay and be brought down. Our last brought down, but our middle needs to be split up using these grouping method, where we say the negative 7x came from a negative 18x and came from an 11x. These two numbers get our x term coefficient. They tell us where this came from and who it came from. And the reason that we split that up is because all of a sudden we can say, oh, sweet, let's group these into binomials and let's factor out what's in common, if possible. And it should be possible if we've done it correctly. What factors out of 3x squared and 18x? 3x. We should have an x minus 6 left over. What factors out of 11x minus 66? And we have an x minus 6. What factors away from these two groupings? What's the same?
3x.
No, what's the same? The x minus 6, so we can pull out an x minus 6. Some of you have different tricks, different ways that your brain has dealt with what to do. But technically we're factoring out the x minus 6's and leaving who's left. And as you notice, it's going to be the exact same as that one. Multiplication is commutative, so it could have been in either order. The last one, the the table method, it's going to be a little different than yours, Lauren, just because you realize yours is this method just right. The table method has us thinking through both 3x squared and negative 66. So this is the actual, well, it is a table method. There are actually multiple ones. But this one has us looking at 3x squared and negative 66. So for 3x squared and negative 66, 3x squared could come from 3x times x and could come from 1 and 66. And we could either try to do 3x times 66, 3x times 66, or 1 times x. Guys, would 198 and 1 ever make our negative 7x?
No.
No. So then we could go ahead and be like, well, that's not a valid option. Now we could go ahead and just rewrite this and just cross that one out, or we could go ahead and right here actually do our, let's switch it, 66 and 1. Would 3 and 66 make negative 7? Nope. Just gives you more of a visual of the guess and check method, basically. What's another way of making 66? 3 and 22. Does 3x and 22? That'd be 66 and 3. That doesn't make negative 7, right? You could switch it and do 22 and 3. Does 9 and 22? Ooh, maybe. 22 minus 9 is 13. 13, close, but not quite. So what's the other way of making 66?
33.
We could do 33 times 2. Or we could get all the way to 11 times 6, 33 and 6? No. Or 6 times 11. 18 and 11. All of a sudden, we're good. With this one, the 18, we want that one to be a negative. This one, we want to be a positive. And so we can go ahead and do 3x. I don't like the way the signs showed up on that one. We know the 3x needs to get multiplied by the 6, and the x needs to get multiplied by the 11. You actually end up writing it like this. Just the way I did my signs looks funny, so it doesn't really help you guys. And I apologize for that. There we go. We need this guy to be a negative, and we need that guy to be a positive. There we go. And then we have our 3x plus 11 and our x minus 6. But this one takes some getting used to. It basically use the idea of guess and check method. You don't actually have to erase things every time. You can write new combinations until you find the winning one. It just basically is a way of avoiding the whole grouping dilemma. But as long as you remember to take this variable and split it up using these two, the grouping method will always work. Just sometimes this number gets big and it gets hard to do mental math with. But it doesn't make you do like trial and error as those two methods do. Okay? How many of you guys would say that you naturally use the guess and check method more, the X method more, or some variation of the X method, and then the table method? I'll use the X method, but realize that if you're trying to do factoring mental math, like in the sense of get to the point where you've mastered factoring, able to do it quickly without showing lots of work, the X method isn't going to ever get you there. It's going to get you right answers, and so that's fine. You don't have to do factoring mental math, like in a mental math way. But if you're trying to grow in your understanding and get faster in your ability to solve, cut it. So you have to be willing to do the work. But as long as you're willing to do the work, it'll be okay. Joe, as you negative 11 over 3?
Yeah. Like 3x equals negative 11, so x equals negative 11.
Oh, I'm getting the work up first because we actually haven't finished the problem. I'm just making sure we can factor. So give me 1 second on that. I noted the x here on out, so I'm going to go ahead and split this guy up into negative 18. 11x 63. As long as you guys have your factors, you should be good finishing the problem. The problem was technically to find the zeros, so the factoring wasn't the final solution. The factoring was the means to the solution. Let me go ahead and get the factoring up here really quickly. X minus 6 plus 11 times x minus 6. 3x plus 11 is what most of you guys probably did. But all along, that's been equal to 0. Because theoretically, at the very beginning, we had something like y equals, you were supposed to find the x-intercept or the zeros. So now, Joe, wait, we're not done because we still have. So as we do that, we will end up with x equals negative 11. Right points. Does that make sense? Once you guys have it, go ahead and close up those homework spirals. Get out your notes section 1 point to the end. Time for us to finish it. Thanks for hanging in there, but I know that factoring is a weakness from Algebra 2 because you saw such harder factoring problems, but hopefully you got a little bit better at it so that as we do it in pre-calculus, maybe I'll have to remind you from time to time, but hopefully you'll become masters at whatever method you use. And if it needs to show some work with the X method, I don't mind. I don't mind. Just you need to be willing to put in the effort. This is what we did yesterday. Symmetry was the topic that we ended with. There's symmetry and one more, and then we're done. Symmetry and one more. I want you guys to go ahead and grab out some sort of colored pen or highlighter. Because for each of these symmetries, for x-axis, you're going to want to keep in mind this point, x negative y. For y-axis, you're going to want to keep in mind negative xy. And for origin, you're going to want to keep in mind negative x, negative y. And you'll see why in just a second. But first of all, let me show you graphs that illustrate each of these symmetries. Just example graphs. It's not like these are magical in any way, shape, or form. They just show or illustrate these types of symmetries. Did I ask you yesterday? I don't think I did. What's a common animal used to illustrate symmetry? A butterfly, yeah. A butterfly is like the most common one. A butterfly. Because when a butterfly is like, well, I guess when it's resting, usually the wings are out. But when the wings go up, sure, there are imperfections here and there on butterflies or on their wings. That's true. But don't make them perfectly symmetric. But if you think about their body as like the axis of symmetry, and then their wings on either side, that shows a good illustration for symmetry. So x-axis symmetry, the x-axis is the line about which the two sides could fold and meet. Y-axis symmetry, the y-axis is the line, the axis of symmetry about which the two sides could fold, or the entire figure could fold, and the two sides meet. And origin is the weird one. For the origin, it's really just a point where the symmetry is around, but you can think of it as taking one branch, one part of the graph, and folding it both over across the y and down across the x. And maybe if you look at those points I circled, it kind of makes sense why the last one, if it has to go both over and down, why the x is negative and the y is negative. Because it has to, in a sense, kind of do both of the other two at once. Symmetry, there's a graph with some sort of line or point, origin's weird, about which one branch would match the other as it was folded on the axis of symmetry. Now off to the side, I'm going to kind of write like a few steps as far as how I would say to test for each of these symmetry. So symmetry is the big idea. But how to test for symmetry. I'm just going to shorten it SYMM. Let me go ahead and do page width. Let's see how much I can fit. But the letters start to get kind of small, so I want you guys to be able to see it. I'll scroll down in just a second if you're still missing origin symmetry. So how to test for symmetry. Plug each symmetry's corresponding point into the, do you guys know that FN is an abbreviation for function? Do we know that? Plug each symmetry's corresponding point, so x-axis, y-axis, origin, into the function separately. Number 2 is to simplify. And number 3 is to compare the results with the original function. Compare the results with the original function. I think I have room to write out original. I didn't think I did at first. And here's the idea. If they're the same, then the symmetry exists. And if they're different, the symmetry, whichever one you're checking for, does not. If, when you compare the results after simplifying, after plugging in the corresponding point, if you compare the simplified form with the original function, if they're the same, if they match, sweet, it has that symmetry. If they don't match, nope, that symmetry does not exist. So that's why I circled each of those highlighted points. Let me go ahead and zoom out so that we can see that bottom graph if you haven't gotten it yet. But I've circled each of those corresponding points because they should work in the original function just as well as the original point xy. They should work just as well. And the way you can see them working just as well, if the symmetry exists, is that after plugging in and simplifying, the function should go back to what it was at the beginning. Now let me go ahead and show you an example. This might be too small. Let me see. I think we can do it. I'm going to move this to another page, though, really quickly, just for sake of space. This is what the book says, and it's not bad, and you could use it, and maybe some of you did in homework last night if you tried to keep going. It's not bad. But my way here will do the exact same thing. So we have the function x squared minus 4. Some of you know that's a parabola shifted down 4. Maybe that gives you all the information you need to know about what symmetries it has or doesn't have. But for our purposes, there are way more complicated graphs than this. So we're going to go ahead and use this easier example to test out our method over here. Okay? So we're going to test for x-axis symmetry. We're going to test for y-axis symmetry. And we're going to test for origin symmetry. We're going to test for x-axis symmetry, y-axis symmetry, and origin symmetry. For x-axis, we're going to use the corresponding point negative y. Y-axis, we're going to use the point negative x, y. In origin symmetry, we're going to use the corresponding point negative x, negative y. And as we think through each of these three, we're going to be plugging into this function the y value to the y spot and the x value to the x spot. The y value to the y spot and the x value to the x spot. Remember, anytime you see a variable in an equation, that variable is really just a placeholder. It's just saying, hey, something could go here. So I put parentheses around it to be very particular when I plug in that I don't make mistakes. Now you guys should have those steps written down. Let me go ahead and go to our example so we can zoom in and do the work a little bit nicer, a little bit more spread out. So for x-axis symmetry, you guys all there to where we're plugging in? Okay. For x-axis symmetry, we're going to go ahead and take the pattern output or y equals input or x squared minus 4. And we're actually going to do that for all of them. We use the exact same equation for all of them because it's our original function. But what we plug in is going to change every time. Maybe not a lot, but at least in some way, shape, or form. First one, we're plugging in negative y, x. The second one, we're plugging in regular y, negative x. And the last one, we're plugging in negative y and negative x. You guys get what I'm doing? Taking the function, taking each corresponding point and plugging it in the y spot and the x spot. What does step number 2 say? Simplify. Okay. Well, what does simplify? Well, 1 times negative y is negative y. X squared is, well, x squared minus 4. Y is y. Negative x squared is negative x times negative x. Positive x squared, you guys agree? And then this last one, 1 times negative y is negative y. Negative x squared is positive x squared. We're supposed to take each of these simplifications and compare them with the original at the top. Which of them match and which of them don't? Who matches? Only the y-axis. Who matches? Only this one. This one, some of you might have been like, divide everything by a negative, and you're right. The y would have stayed positive, but then these signs would have flipped. It wouldn't be the same. If it can't match, it doesn't have that symmetry. And if it can't match, if it can't be the same, it doesn't have that symmetry. So at the end of the day, which symmetry does this function have? Only y-axis symmetry. Now once again, I did say a second ago, some of you guys, well, let me write it first. It only has y-axis symmetry. Some of you guys can look at this function and say, he's a parabola, he's been shifted down 4. Let me give you a quick visual. An x squared, 1, 2, 3, 4. Roughly. Oh, hey, he folds over the y, not the x and not the origin. Okay. But what I said was there are harder functions that maybe you can't visualize as easily, and this trick, these tests still work. Does that make sense? Okay. So let me show you what the book does. Because the book, you might have seen a second ago, I had like this copy and pasted table from the book, and it's good and all. It's not bad. What it does is it goes ahead and gives you sentences explaining the algebraic test for symmetry. But basically it's what we just did. Because when they say there will be x-axis symmetry, when replacing y with negative y yields an equivalent equation, what we did is we said x-axis symmetry, plug this point in, and who is the only guy that actually changed? Yeah, x stayed the same, y became negative y. So technically when they say replace y with negative y, well, it's basically what we were doing. And they're going to say y-axis symmetry is going to exist when replacing x with negative x yields an equivalent equation. They're totally right, because that's what we did. We replaced x with negative x. We just kept y the same. Then last but not least, they said origin symmetry is when you replace both x with negative x and y with negative y. You simplify, it's an equivalent equation, which is what we did. Oh, sorry. Replacing x with negative x and y with negative y from the original. So that's ultimately what we're doing. I don't know if we have time today for me to illustrate as to why I like these corresponding points a little bit better than like the sentences in the book. The sentences in the book aren't bad. They really aren't. And some of you, maybe it'll work better with your brain to actually read it out and try that. But the corresponding points are really nice too. And I'll try to show you tomorrow the visualization for why I think those are good as far as for memorizing. But for right now, there is one more topic in 1.2. And then we're done. So, standard form equation of a circle. Last topic for today, and the last topic for 1.2. The standard form equation of a circle. You guys have seen it before, it's probably just been a little while. So let me just give you a few reminders about how this equation works before I show you how an example could get a little tricky. There are two main things to know about a circle. If you think back to when you made circles in geometry with a compass, right, had the pointy end and had the pencil, and then you stick the pointy end, and then you make the distance what you want it to be, and you go around. A circle is a collection of points, a set distance from a center. The center is important, and the radius is important. The center is going to be whoever is in the h and the k spot of this given equation, x minus a squared plus y minus k squared equals r squared. The radius is going to be r, who's going to be the square root of whoever's on this other side of the equals. But what gets weird when we get down to this example down below where it says, hey, here's some information, make me an equation of a circle. What's the easy thing to plug in from what you guys, oh, I didn't write radius. Low scale. Okay. What's weird about what they did or didn't give us in this example? Yeah, they didn't give us the radius, but they did give us enough information to get the radius. They did give us the center. That's kind of nice. When we go to plug in, all right, x minus center. So let me go get that point and plug it in. The problem is I don't know the radius yet. The center is going to be, careful, they give us 2 points, but only one is the one I can plug in. The center is going to be the point negative 1, 2. Negative 1, am I making that positive? Right, if you're subtracting a negative like subtracting a negative will be adding. Or negative times a negative is a positive. Both ways work. But how am I going to find r? Because r is the exact same thing as the distance between the center and what we would call a solution point. A solution point is a point that's on the outermost edge of a circle. The distance between the center and any solution point will always be the radius. So you're just going to have to go back to section 1.1 and say, I can equal the square root of, now you could do your nifty little x2 minus x1, or you could make our little triangle like I was showing you. The little triangle is going to go over 1, then 3, which is 4. Go up 2. So you're going to have 4 squared plus 2 squared, which is the square. Now some we actually need to take this r and plug it in. Maybe it'll make a little bit of sense why we don't change it, because then we can get x plus 1 squared plus y minus 2 squared equals, and a square root squared becomes just the underneath part. Why did I show you that? Well, because you might be making easy circles or you might be making hard circles or a few in between. Keep in mind your distance formula and you'll be fine. All right, cool kids. Homework number 2 due tomorrow. Make sure you get your pictures in by 7 a.m. Happy Thursday.